Alrighty, welcome back to Math 107, and I believe we're at Lecture 14A, according to my calculations. Hope that's true. This is the beginning of Test 3 content, and we're going to begin Test 3 with Chapter 4, Section 4, Logarithmic Functions. And I'm hoping that in Lecture 14A, we cover both Chapter 4, Section 4 and Chapter 4, Section 5, Properties of Logarithms. All this kind of goes together. However, I don't usually get as much covered as I hope, which is okay. We will get it done. Now, let me just back up a second and say how we got to our section, Chapter 4, Section 4. You'll recall that in Chapter 4, Section 3, we studied all about exponential functions. Y equals a to the x, or our natural exponential function, which is y equals e to the x. And we looked at domains and ranges and asymptotes and how you solve exponential equations. Well, interestingly, in this book, you probably wondered, why did you spend so much time on 4.1, composition of functions, 4.2, one-to-one functions and inverse functions, and then all of a sudden we're talking about exponential and log functions. So, in section 4.4, logarithmic functions, the first thing we're going to do is look at the exponential function, observe that it is one-to-one, has an inverse function, go to the inverse function, give it a name, which is called the log function. So the exponential function and the natural log function are simply inverse functions of each other. And you remember that's just a business of creating new functions when you're able to come up with an inverse function. Okay, so let's just do a little preview of Chapter 4, Section 4. We're going to cover all these objectives. First, once we have an understanding of what a log function is, where things coming from, we want to be sure that we can convert. This says change. Convert's another word. Convert exponential expressions to log expressions and logarithmic expressions to exponential functions, expressions. We've got to be able to convert from exponential form to logarithmic form and back and forth. They're going to work with each other. That will be especially important when we get over in Chapter 4.6, I believe it is, where we start solving exponential equations and logarithmic equations. We're going to have to be able to convert back and forth. Evaluating logarithmic expressions. How are you going to get the value of a logarithmic expression? And that really is going to be a conversion back to exponential form. We want to, of course, always talk about the domain of a log function. If you don't know what the domain is, then you don't know what values make sense. And the graph of a log function. And then in number 5, we're going to start solving some very simple logarithmic equations. But when we get into 4.5, I think it's 4.5 and 4.6, we're going to be solving more interesting logarithmic equations. Okay, so I wanted you to know that's where we're headed in section 4.4. All right, so the first thing we want to do is go back to what we already know. So we are in Chapter 4, Section 4. Well, let's do a recall. Let's go back and just sketch the graph of y equals 2 to the x. Y equals 2 to the x. All right. What does the graph of this look like, everybody? Y equals 2 to the x. Just had it on your test.
Exponential growth.
Say it out loud.
Exponential growth.
It's an exponential growth curve. What's the y-intercept?
The y-intercept's 1.
0, 1. And as x gets bigger and bigger, the y flies off to infinity. And as x gets smaller and smaller, it approaches the y-axis. Okay. I'm going to call this f of x. So let's get the domain of this again. This is all review. In case you can't tell, this is review. My domain is x is what?
All real numbers.
All real numbers. My range is, what's my range?
All real numbers greater than 0.
Y is all real numbers greater than 0. My asymptote is?
Y equals 0.
Y equal to 0. Okay? Now, this function is 1 to 1. Why is that? How can you look at it and tell it's 1 to 1?
Horizontal line.
Okay, passes the horizontal line test. Passes the horizontal line test. Okay, because it is 1 to 1, because there is an inverse function. Okay, if I know the graph of y equals 2 to the x, do I know how to graph its inverse? Sure, it's just a reflection across the line y equals x, correct?
Oh.
All right, let's get our domain and range of our inverse function. Let's go ahead and write it like this. What is the domain for the inverse function? Okay, remember the range of the original function becomes the domain of the inverse function. What is, remember this? Because you're interchanging x and y. What is the range for the inverse function? Y is all real numbers. What is the equation for the asymptote?
Y equals 0.
Nope. You're interchanging x and y. What is it?
X is equal to 0.
X equal to 0. X equal to 0 is the y-axis, right? So we'll put a little dotted line here. X equal to 0. So for my inverse function, it's only going to be in the first and fourth quadrant as x is greater than 0. The range is all real numbers, so that will be first and fourth. And here's my asymptote. Remember to sketch the inverse. If you know the point 0, 1, then what point do you know on the inverse function? 1, 0. Okay. And here, as x approached infinity, y approached infinity. So changing that around, as y approaches infinity, x approaches infinity. You're just interchanging every part, or you're just like flipping across the line, y equals x. So the graph of the inverse is just going to be a reflection like this. See, this is as x goes to negative infinity, y goes to 0. Let me write that down. As, on the blue, the function, as x approaches negative infinity, y approaches 0. So for the inverse function, as x approaches 0, and we got to be on the right side of 0, and this was 0 from the positive side, by the way. As x approaches 0 from the positive side, y is going to approach negative infinity. See how I interchange that? So it matches up. All right, so this represents the inverse function. This represents the graph of the inverse function. All right, but what is the name for this inverse function? Well, let's look over here and see if we can't figure this out. What is the name for the inverse function of y equals 2 to the x? Well, when you tried to solve for an inverse algebraically, didn't you interchange x and y? Interchange x and y? So you interchange x and y. And then you have to solve for y when you were looking for an inverse. Well, the problem is, without a definition, we don't know how to solve this for y. Okay, so if you'll go to your book on page 435 in your book, page 435. Page 435. At the bottom of page 435 is a definition. There had to be some way to give this thing a name. It's not anything but a name. All right? So, at the bottom of page 435, it says, the logarithmic function to the base a, where a is greater than 0, a not equal to 1, is denoted by y equals log to the base a of x. Y is the logarithm to the base a of x. You usually say log to the base a of x. Is defined, so it's a definition, somebody gave it a name, by y equals log to the base a of x if and only if x equals a to the y. All right, so you're probably going, how will I ever get that straight? Or that's what I did the first time I saw it. How do I keep that straight in my mind? How to go from y equals log to the base a of x to x equals a to the y? And I'll tell you how my little brain did it. See, this is a base a with a logarithm. When you have an exponential equation, remember you call a the base and y the exponent? So the base a for the logarithm is the same as the base for the exponential equation. And I always like to think of it visually so that I don't miss it, as if it's in this form, it's like I take the little base a over here, that didn't work, use this pencil that you probably can't see. It's like I take this a across the equal sign and push the y up. So you got a to the y equals x. That's how I keep up with how to convert from log form to exponential form, because the base for the logarithm is still the base for the exponential equation. Y is the exponent, and you'll notice that at the bottom of the page your author says a logarithm is merely a name for a certain exponent. Y is an exponent. Y is an exponent. So the base to that exponent is x. Okay, so because I have this definition, I can now give my inverse function to y equals 2 to the x a name. So by definition, notice this is a base 2 for my exponential. So I would say log to the base 2 of x equals y. And that is my inverse function. Okay, so what I have on the previous page, this graph, we give it the name inverse function equals, or my y equals, log to the base 2 of x. So the name for the inverse of y equals 2 to the x is log to the base 2 of x. Okay? Now let me make a couple comments about this that are very, very important. Go back up here where we did domain. Domain. For my inverse function, which is log to the base 2 of x, my domain is that x has to be greater than 0. X has to be greater than 0. This x, by the way, is called the argument. Whoops, can't spell it. Argument. Having a bad day. The x part is called the argument. This x value here is always greater than 0. So when you're looking for a domain, whatever your argument is, that argument must be greater than 0. If you punch in your calculator log of a negative number, you're going to get an error message. That's because your log of some argument has to be defined to be greater than 0, and that came from that part right there. Okay? What else do I want to tell you? Let's just do a transformation and get domains, ranges, and whatever. Okay, let's sketch a graph. Let's sketch the graph of the function y equals 2 plus the log to the base 3. I'm just going to give it a base 3. They're all going to have basically the same shape. The main thing we're going to keep up with is domains, asymptotes, intercepts, if we can find them. Okay, log to the base 3, x minus 4. Okay? All right. And we're going to say what's going on here. Let's first get the domain. Based on the information we just talked about, whatever you're taking the log of, this argument always has to be greater than 0. It's defined only when it's greater than 0. So when you're looking for the domain, you have to say x minus 4 is greater than 0. So x then will be greater than 4. If you were doing a translation, based on the way this is set up compared to the graph of y equals log to the base 3 of x, this would tell you that you're going to shift to the right 4 units. This little part right here tells you you have a horizontal shift to the right of 4. And that's where you're going to get your domain there. X has to be greater than 4. Okay. What does this plus 2 tell you? What did that tell you, everybody? That's going to be a vertical shift up of 2. Okay. Oh, let me back up. If my domain is x is greater than 4, do you immediately know the asymptote? Okay, remember when you were graphing y equals log to the base a of x, it looks like this, and remember that the y-axis, x equal to 0, was your asymptote. So if we shift it to the right 4, what's that going to do to your asymptote? Shift it to the right 4, so x equal to 4 is going to be your asymptote. Okay, let's see if we can sketch the graph. These are usually really easy to do once you've got your basic graph in mind. Okay, we're going to shift everything to the right 4. There's my asymptote. All right. And so first, if I graph y equals log to the base 3 of x minus 4, it would go through the point 5, 0. It would just come around like this. But really, this shifting up of 2, I'm just going to go ahead and shift it up 2. I move everything over 4. You know that it would normally go through the point, this is 1, 0. This would normally go through the point 5, 0. But now what's it going to do? It's going to go up 2, so this point goes up 2 with it, correct? So a point on the graph should be 5, 2. Okay, because it would have normally gone through 5, 0 when I shifted it over. But now this is going to go up 2. Okay, and the graph has still got to approach this asymptote. I don't know what the x-intercept is at the moment, but later we will learn to find the x and y-intercept. Yeah?
Why would it, oh, never mind.
Go ahead.
No, I was going to say, why wouldn't it go through, 5, 3, but then I remembered that it was the inverse.
Okay. All right. I'm going to check this. I haven't given you the identity yet to tell you this. Log to the base 3, if I put a 5 in for x, 5 minus 4 is 1. Log to the base 3 of 1, actually log to any base of 1 is always going to be 0. So if I put a 5 in there, that gives me log to the base 3 of 1, which is going to be a 0. 0 plus 2 is 2. So the 0.52 is on the curve. Later we'll be able to find the x-intercepts once we learn to solve these kind of equations with the y being 0. Okay? All right, so you're going to, when you're sketching some of these graphs, you're just going to do our transformations like we've been doing. But for log functions, key things you want to keep up with are the asymptotes, your domain. You do your domain and then you got your asymptote. And then follow around that little point 1, 0, because it's the part that's going to be shifted around or multiplied times or whatever. Okay? All right. Well, let's get back to converting from exponential form to log form, which is we're going to be working on. And so the instructions might be something like this. Convert, I believe your book uses the word change. Convert from exponential form to logarithmic form. From exponential form to logarithmic form. Okay, here's the example. We'll take something pretty easy. 2 to the 4th equals 16. to the fourth equals 16. That's an exponential equation. Why is that called an exponential equation?
Because it has a value raised to the power.
Yep, it's got a value, namely 2, raised to an exponent. This is an exponential equation. Convert from exponential form to logarithmic form. All right, so this is the exponential form. So we're going to convert to log. Based on the definition you just looked at, and hopefully you still have your book open to page 435. All right, it's going to be log to what base? 2 of what? 16 equals 4. Check. Remember that you keep your same base, and the answer with the log, the equals to, is actually the exponent. So log to the base 2 of 16 is equal to 4. What about, let me see if I have another one that I want to do. Y'all do that one so fast, I don't know. Let me put an x in there. E to the x is equal to 10. That's an exponential equation. It happens to be a natural exponential equation because e is called that natural exponent. Okay. E to the x is equal to 10. That's going to be log to what base? E of 10 equals x.
So that's 10 to the, that's the power?
The what?
No, the 10.
The 10 is the argument. Natural log to the base e of 10 is equal to x. X is the exponent power. Yes?
Why don't we just write it as like ln instead of
Okay.
e?
So log to the base e has a special name. It is called the, what's it called? Natural logarithmic function. Log to the base e. And the notation for that is ln. When you see a ln, it means log to the base e. All right, let's zoom in on the calculator here. Remind me again what e is about equal to?
2.71.
Okay, 2.72 I think. E is about 2.72.
Yeah, it's like 2.71.
All right. So if we want to use our calculator and get a good approximation for natural log of 10, the natural log usually is a button right there on your calculator somewhere. All right, so we'll just put in natural log of 10. You're not seeing it. Can you see that? All right, natural log of 10 is approximately equal to 2.30, looks like. Natural log of 10. All right, just as our little check, let's check out 2.3 raised to the, right here, excuse me, e. E is, which is about 2.72. And let's raise it to the 2.3 power. All right, so I'm just substituting back into e to the x equal to 10 as my little check. All right, so 2.72 raised to the 2.3, and as you know, everything has been rounded here, so we're not going to be exactly equal to 10, but it should be pretty close. Equals 9.9886. We did a lot of rounding there. But that was my little check to show you that the natural log of 10 is approximately 2.30, meaning e, which is about 2.72, raised to the 2.30 should give me pretty close to 10. Everybody good? All right, let's do another example. How about 10 raised to the third is equal to 1,000? Let's convert that exponential equation to logarithmic equation. It would be log to what base? 10 of 1,000 equals 3. All right, somebody impress me and tell me what log to the base 10 is called.
It's a basic log.
Yeah, but basic log, it also has another word for it. Starts with a C. O.
Complex.
What?
Complex.
No.
Conjugate.
Complex is a good word to try. Common log.
Constant.
Oh, Tom.
It's called common logarithm. Common logarithm. Anybody got an idea why it's called common?
Because it's
10
log
is
base
just
10.
that.
Wait, what'd you say?
Like I was going to say log 10, that's like what it's all based on.
Yeah, so why is it called log 10? What were you going to say, Aaron?
It just makes it easy.
Why does it make it easy?
Isn't that
Because
what
it's log 10.
our numbers are? Base 10?
Our number system is based on base 10. And before the days of calculators, which was when I was in school, we couldn't do all these complicated arithmetic examples when you had things raised to power and all that. So we had to convert to common logarithms and use tables to do all our calculations, and that's why you use common logs, because it fit our number system. All right, so to write a common log, you just go log 1000 equals 3. So when you don't see a base with log, it's understood to be base 10. When you see ln, that stands for natural log function, and that's understood to be base e. All right, you have a log button on your calculator. Log button, right there. Okay, so if you put in common log of 1000, that's basically saying what power do you raise 10 to give you a 3? Give you 1,000, sorry, and the answer should be 3. So when you hit the enter button, there's your little 3 right there. That says 10 to the third power is 1,000. Okay, so common log is saying what power of 10 gives you 1,000. All right? Everybody good so far? Okay, so what we've done is exponential equations and converted to logs. We have defined the natural log function. Remember, the natural exponential function is used in just about every physical problem to describe some kind of growth problem. So therefore, natural log functions would be used a lot. Common log is not used quite as much as it used to be, but their properties still hold for plenty of properties still. Applications go for natural common log. Excuse me. Okay, let's convert the other way. Let's convert from logarithmic form to exponential form. Okay, we'll just make up something. Log to the base 3 of 81 equals 4. Let's see if that's true. Making it up on the spot here. All right, why is this called a logarithmic equation? I want you to say it. So when you get on the test. It's got a log in it, right? And it's got an equal sign. So that's called a logarithmic equation. And we're going to go to an exponential form of this equation. So what is my base? 3. 3 to what power? 4th power equals 81. 3 times 3 is 9, times 3 is 27, times 3 is 81. Okay? All right, how's that, everybody? All right, let's look in the book and see if I've covered everything. This section's really, this particular section just has some basic things in here. Change from exponential to log and back and forth. Evaluate logarithmic expressions. Okay, we'll look at some of the exercises on that. Domain of a log function. What has to be true about your argument? Has to be greater than 0. Graphing the log functions, this has to do just using your transformations. If you know the graph of y equals log to any base x where it's defined, it's going to be real simple to put in your asymptotes. And then solving a few equations. Let me flip through the pages and make sure In the middle of page 437, we mentioned this. Domain of your log function is the range of the exponential function. That's because they are inverses of each other. The range of the log function is the domain of the exponential function. A lot of people don't get it, that they're just simply inverse functions of each other. On page 438, this is the little exercise we just did, except we used a base 2 and they're just using a base a greater than 0. There's the graph of your exponential function, and then they graphed the inverse function and gave it its name. Okay, don't forget to be wearing out your book. Page 439 talked about the properties of log to the base a of x. The domain, that means your argument is positive real numbers. Whatever that argument x is, whatever you're taking the log of, has always got to be greater than 0. Your range is all real numbers. If you're just doing a basic log to the base a of x, your x-intercept will always be 1. Of course, there is no y-intercept because your asymptote is x equal to 0, vertical asymptote. Okay, it's talking about increasing and decreasing. That depends on your value of a, because when we had a being a number bigger than 1, you had a exponential growth for exponential functions. So when you do the inverse, which is the log function, your log function will increase for a bigger than 1. And you remember when you had an exponential function between 0 and a half, that was your decay curve. I can't do it backwards. Decay. You know how the decay curve looks. So it was decreasing, and the same thing when you did the inverse for the log function. If you have a base at y equals log to the base a of x, you definitely are going to have that point 1, 0, and your curve is continuous and smooth. All right, in the middle of page 439 is where they define the natural logarithmic function. That is a base e. Natural logarithmic function. And it occurs frequently in applications, very frequently in applications. Okay? Let's flip the page. Those just graphing transformations. Page 440 in the middle. 440 in the middle. This is where you see your common log function. That's just your log to the base 10. Just your logs to the base 10. Okay? If you look on the top of page 441, that example, y equals 3 log x minus 1, you know that is a vertical stretch of 3 by factor of 3. And you know that it's a horizontal shift to the right of 1. Notice that when they get ready to graph, the very first thing they're going to look at is the domain. That helps you know right away where you're going to put your asymptote and start. I kept saying your argument has to be greater than 0. So for this, your domain is x greater than 1, which automatically makes your vertical asymptote x equal to 1. Okay, this didn't have a vertical shift, so you know that it's like plotting the point 1, 0, but everything moved over 1, so you'll plot the point like 2, 0. And that 3 is just your stretch, which means it's going to go up a little bit faster. Okay? And then the last objective, which is at the bottom of the page, is solving logarithmic equations. And what happens is, whenever you're solving a logarithmic equation, such as a, you're going to have to find a way to get rid of the logs so that you can get to the argument. So if you'll keep in mind, if I have a log equation and I need to get to that argument, I'm going to have to go to the exponential form. And later in section 4.6, when we have these exponential equations that we got to get to the exponent, we're going to have to go to the log form. The logarithmic form and exponential form are going to work together very nicely for solving equations. So if we look at example 8, I'm going to talk through this and then we're going to do a bunch of problems in the exercises. If I need to get rid of that log there because I'm solving for x, your brain is going to go, the only way I can get rid of the log there, because it's not log times, it's log of. It's representing a function. Log of this thing is to switch it into exponential form. And if you look at the solution right here, the base 3 came over and the 2 was the exponent for the 3. So once you get it right here, life is great. You're just going to have an algebraic equation to solve. Okay, so if you have a logarithmic equation, the variable is part of the argument or your base, like in B. Your brain's going to go, I got to get rid of that log somehow. You always go into exponential form. That's the trick of the trade. And then you can't miss them. That would be nice, wouldn't it? Alrighty, so I think that we are ready to work a bunch of problems in the exercises. I'm on page 444, and I just went through and picked some that I thought looked fun. Alright, so I'm on page 444 in the exercises. And the first problem we're going to look at is number 16. This will probably be too easy. 3 to the x equals 4.6. It says change from exponential to logarithmic. Since it says an x right here, we're probably looking for a way to define what x is when we're changing this. All right, I need you to verbalize it so I know you're getting it. This kind of equation is called a exponential. You don't see the word log there, so it can't possibly be called logarithmic. Exponential equation, you have a base with a variable exponent. Exponential equation. All right, so to switch it to, I wanted red, try green. To switch that to a logarithmic equation, it's going to be log to what base? 3 of 4.6 equals x. By the way, this is called an exact value. Exact value. Because when you plug and chug this in your calculator, and we're going to have a formula very shortly for bases other than E or 10, when you plug and chug this in your calculator, you're going to get an approximate answer, not an exact, because it's going to be a decimal that's not going to repeat and terminate. Okay? So on tests, a lot of times I will say leave it answers exact. So this is an exact answer. Okay? Exact value. All right. Number 16 was a piece of cake, right? So let's go to number 20, see what that looks like. Number 20. E to the 2.2 equals m. What kind of exponential function is this? What's the word? Natural exponential. Exponential, right? There's not a log there yet. All right, let's convert that to log form. It's going to be log to what base? E of... Yeah, m equals 2.2. And what's the symbol for log to the base e? ln. And what is that thing called? Everybody say it. Natural logarithmic function. That is the natural logarithmic function. Okay? ln represents log to the base e. All right, number 27. Which is top of next page. We now have log to the base 2 of m equals 1.3. What kind of equation is this? What's it called? Logarithmic equation. And the instructions are to express in its equivalent exponential form. Okay, let's switch this to exponential form. What's it going to be? 2 to the 1.3 equals m. Okay, these are equivalent equations. I'm on number 27, I thought. Log to the base 2 of m equals 1.3. So 2 to the 1.3 is equal to m. These are equivalent equations. Everybody got it? Let's go to number 32. By the way, you could put in your calculator if you wanted to approximate m for some reason. We could say 2 raised to the 1.3. Just want to get a feel for what that is. That's about 2.462. approximately, if you wanted 3 decimal places. Okay. Number 32, we have lnx equals 4. What kind of equation do I have here? Natural logarithmic equation. Let's convert it to an equivalent exponential equation. What's it going to be? E to the 4th equals x. What's e to the 4th about equal to? E raised to the 4th is approximately equal to 54.598. Because e is about 2.72, so it's about 2.72 raised to the 4th. Oh, e to the 4th is called an exact value. And exact values are wonderful. I was just trying to give you a feel for what that was approximately equal to. All right? Everybody good? Number 38. Number 38. Find the exact, I'm going to write those words. Find the exact value. Okay, exact value on any test means no calculator approximations. No calculator approximations, exact value. Number 38 says, find the exact value of log to the base 1/3 of 9. Find the exact value of log to the base 1/3 of 9. So we're saying, what is this thing equal to? How are you going to go about figuring out the exact value for this? Say it.
I was just gonna say, can you? I don't know. I really don't.
It's okay if you say wrong.
Do you? Go ahead.
No, you go.
I was gonna, like you did one of the problems. It's like 1/3, and then I think. Go ahead.
Well, I was just gonna say take the 1/3 and raise it to x equals 9.
All right, so that's exactly what you were trying to say. You just didn't have confidence. Okay. All right, so the problem is you're supposed to try to find our exact value of this. You have no clue what this is approximately equal to, so it's got a log in it. You're going to remember if you're in a log equation and you don't have a clue, try switching it to exponential and see if life would be better. So we're going to convert this, just like you said, to exponential form. So it would be 1/3 to the x equals 9. Well, is that going to help me? I'm trying to solve for x, and this is an exponential equation. What you going to do?
I don't believe it. That's the exact value, isn't
I think we can go further. What are you going to do?
You're gonna make 9 into an exponential, like 3 to the 3.
You are very good. You're saying, I have an exponential equation. I've learned, can I get like bases? And you just notice that 9 is the same thing as 3 squared. Is there a way you can write 1/3 with a base 3? 3 to the negative 1 equals x. So now, power of a power, I have 3 to the minus x equals 3 squared. This is what you did in section 4.3, I think. The bases are the same. So now we can set the exponents equal. So x then has to be equal to -2. And we know that 1/3 to the -2 power would be the same thing as 3 squared, which is 9. Okay, very good, very good. Everybody all right? So when you have a log equation and you're stuck, your brain's going to go, let me try putting this thing in exponential form and see if I can't solve. Is that good, everybody? You want me to wait a second for you to copy that down? All right, I think I can squish the next one in here. The next one is number 44. Same instructions, find the exact value of the natural log of e cubed without using a calculator. Exact values without finding a calculator. All right, so we're going to go, what is this equal to? And everybody's brain is going, this is a log equation, and I don't know what it is. So it's a natural log equation. Unless you've already studied logarithms before, then you probably know an identity right off. Is that what you're thinking about? Well, don't say it. That's a surprise. All right, so if you don't have a clue what to do, what are you going to do, everybody? Switch it to exponential form. So this is really the same thing as log to the base e of e cubed is equal to that unknown. So to switch it to its equivalent form, would that be e to the question mark equals e cubed? The base e to the question mark is equal to e cubed. Now the bases are the same. You know immediately what natural log of e raised to the third is equal to. What is it, everybody? 3. That was too easy. And in the next section, we have an identity to verify that.
Can we just, like, instead of write question mark, can we write X?
Oh, you don't like question marks? Call that an X then. Sure. You can call it a M, a P, a J for Justin, or whatever you want. If you don't like question marks, just put your little X's right there.
I just want to make sure, 'cause, like,
Oh,
I
yeah.
didn't know.
Yeah, you can put anything you want to. Any variable there or letter, be fine. How's that, everybody? Good? Okay, while I'm waiting for some of you to copy that down, go to problem number 50. The question is asking for the domain. Go to problem number 50. Oops. Okay, number 50. We're still on page 445. Number 50, we're just looking for the domain of this function. How are you going to find your domain, everybody? Okay, whatever you're taking whatever the argument of your log is, has to be greater than 0. So x is going to still have to be greater than 0. Okay, let's look at number 52. Probably doing some of the WebAssign questions for you. G of x equals the natural log of 1 over x minus 5. Natural log of 1 over x minus 5. How are you going to start out looking at that domain? Okay, your argument has to be greater than 0. Isn't that a rational expression? Have we learned to deal with telling where a rational expression is positive or negative? Little sign chart. What makes that rational expression exactly equal to 0? I mean unknown. Excuse me, 0 or undefined at 5. Okay, so we'll have to put a little open circle here because x could never possibly be 5 because that's division by 0. All right, if we pick a number bigger than 5, is this expression positive or negative? Positive. If we pick a number less than 5, is this expression positive or negative? Negative. So what is my domain for this expression? X has to be greater than what? 5. What's going to be my asymptote here? X equal to 5 is going to have to be your asymptote. Okay? How are we doing, everybody? Good? All right. Let's flip over on page 446, and the next problem is number 89. Oh, that's a transformation. I didn't want to do that. We've already done that. Let's go to problem number 93. This is page 446. The instructions are to solve for x. Number 93, log to the base 2 of 2x plus 1 equals 3. Okay. Log to the base 2 of 2x plus 1 equals 3. You're solving for x. The thing that I'm hoping your brain is saying is that x is in the argument of the log. The log is getting on my nerves. I've got to find some way to get rid of it. Everybody's going to say, go ahead, go to exponential form. Exactly. So we're going to switch this to the equivalent exponential form. And what is that? 2 to the third equals 2x plus 1. 2 cubed is 8. 8 equals 2x plus 1, and then we'll just fly through this. 2x equals what? 7. X is equal to 7 halves. Okay? All right, next example. I'll just pick number 106. All right, that was a logarithmic equation. The variable was part of the log. It was the argument. You got to find some way to get rid of the log. Okay, number 106 is e to the minus 2x plus 1 equals 13. What kind of equation do you have here? Natural exponential. And the variable is up in the exponent. The variable that you need is up in the exponent. Everybody's brain is going to go, how do you get it out of the exponent?
Switch to logarithmic.
You're going to have to switch to the equivalent log form. So it's going to be log to what base? Log to the base e of 13 equals negative 2x plus 1. Natural log to the base e is natural log, so we have natural log of 13 equals minus 2x plus 1. And if we're looking for the exact value, all we got to do is still solve this for x. So we'll have negative 1 plus log, natural log 13 equals minus 2x. X is equal to negative 1 plus natural log 13, the whole thing divided by negative 2. And of course you could write that as positive 1/2 minus 1/2 natural log of 13. I mean, you could change the form if you wanted to. That form is perfectly good, but some of you like to do like this.
And we just leave it like that.
Sure. You could leave it like this. You could actually go to your calculator if you were looking for an approximate value because you just wanted to check it. Put in the natural log of 13, multiply it times the negative 1/2, add a half, and you get a decimal representation. But this is perfectly fine right here. Everybody good? Okay. I didn't realize that was going to take an hour to do, so we're going to start the next lecture in 4.5 where we're going to get our properties of logs. And we're leading to being able to solve logarithmic equations and exponential. Okay, see you shortly. Oh, yeah. Alrighty, welcome back. We're on Lecture 14B, and we're going to try to cover Chapter 4, Section 5, Properties of Logarithms, and Chapter 4, Section 6, Solving your logarithmic equations using your properties of logarithms, and also solving your exponential equations. So these two sections kind of fit hand in hand, so I'm hoping that we'll be able to get through those. Alrighty, so 4.5, let's go back to what we already know, or should know. 4.5, recall. Okay, we're going to recall that f of x, which is equal to e to the x, has an inverse function. Tell me what that inverse function is, everybody. What is the inverse function for f of x equals e to the x? What kind of log?
Natural log.
Natural log of x. These are inverse functions. All right, now go back in your memory. to in your brain, don't look it up. Let me get the right section though. Section 4.2, when we studied inverse functions. If two functions are inverses, so recall section 4.2, two functions that are inverses. What did you learn about the composition of f and g at x, as well as the composition of g and f at x if these two are inverses? What do you get back? You get back whatever you started out putting in, and in this case you're putting an x in. So if I form the composition of f and g at x, that value has to equal x if they're inverses. Just like if I did f and g at 3 and followed that through, that would have to be equal to 3, or the other direction. Okay, we're going to look at this because it is from this fact that the composition of inverse functions give you x. It's going to bring us to two identities that we're going to commit to memory and use many, many times. All right, so let's first do the composition of f evaluated at g of x, which is f evaluated at the natural log of x. Everybody with me? I'm just substituting there. So what is f evaluated at the natural log of x? E raised to the natural log of x, right? Natural log of x goes in for x there. But because we know these are inverse functions, and we had a theorem that said when you form that composition, this thing right here must be equal to x. So e raised to the natural log of x is equal to x. Remember, natural log is e to the log to the base e of x is equal to x. That's a way that I'm sort of indirectly showing you an identity to memorize. And that is that a raised to the log to the base a of any argument m. It has to be base a raised to the log of base a of m is going to be equal to m. So if you have e raised to the natural log of anything, it's going to be equal to that anything. Here's the example. I could have 3 raised to the log to the base 3 of x squared minus 1. According to this identity, I have the exponential equation with a base 3. I have the log with the same base 3. They're really inverse functions of each other, so they're canceling out the log, and this would be equal to x squared minus 1. Okay. Suppose I have 4 raised to the natural log of x. Do we know what this is equal to just looking at it using the identity? Is this equal to x?
ln.
Is this equal to ln of x?
Yeah.
I only heard one yes. Is everybody saying it? What are you saying? Does this fit the rule?
No.
A to the log to the base a of m?
It's log to the e.
No, it's log to the e.
Okay, so we don't know what this is. Okay, because it doesn't fit the identity. The point is it has to be the exponent base a, the exponential equation, a, base a, raised to the log to the base a. You got to have the a's matching. So we don't know anything about 4 raised to the natural log of x. It doesn't fit the identity. Okay? All right. So that was the composition f at g of x to come up with the identity a raised to the log to the base a of m is m. All right, let's look at the composition g evaluated at f of x. G evaluated at f of x. If you flip back around, f of x is e to the x. f of x is equal to e to the x. Maybe I better write these up here. F of x is e to the x. G of x is natural log of x. Did I get them backwards? No, there you go. Oh, you can't see it. There you go. All right, so we're going with the second part of the theorem on two functions that are inverses forming their composition. Okay, g evaluated at e of x would be natural log of e to the x. Because these two functions are inverses of each other, when you form their composition, they have to equal x. So we really have just shown a new identity to memorize. Identity. And reminding you that natural log is just log to the base e of e to the x is equal to x. Okay, the identity is log to some base a of a raised to the m. Log to the base a of a raised to the m, and everybody says that is equal to m. Okay.
Are the A's the same?
Yes, a has to be the same number.
And the first one too?
Yes, in the first one too, the a's had to be the same number. Exactly the same. All right, the example, if you have log to the base 3 of 3 raised to the 10th, what's that equal to, everybody? 10. What about the natural log of 5 raised to the 8th? We don't know what it is because they have different bases. It's got to, if I have natural log of e raised to the 8th, what is that equal to? Natural log of e raised to the 8th. 8, because that's log to the base e of e raised to the 8th, which is 8. Okay? Got to have the base to the log and the argument the same. Everybody got the two identities? Look at your neighbor and make sure that you do. Everybody got it? Commit it to memory, sleep on it. You're going to have to use it for solving exponential and log equations. Okay. Some properties of logarithms that you're going to have to memorize. By the way, those identities, they're actually calling them properties on page 449. They're calling these properties. We usually call them identities. A raised to the log to the base a of m is m. The base a raised to the log to the base a of m is m. Okay. These are usually called identities in other books. And this is log to the base a of a raised to the r. They used a r instead of an m. There's your r. Okay, and the proof for this was when they looked at the composition of those two functions, just like what we did in class just a second ago. Okay? All right, back up just a little bit above this theorem on page 449. Log to any base a, where it's defined of 1, is equal to 0. Remember, the log graph goes through the point 1, 0. The log of 1 is 0. That's because this is easy to see. If you switch that to exponential form, wouldn't you have a to the 0 equals 1? So log to the base a of 1 equals 0. And what about log to the base a of a is equal to 1? Well, if you've memorized already this identity at the bottom, that's an understood exponent 1, or if you switch it to exponential form, a to the first is a. Okay? All right, but these two, 1 and 2, are your main identities you're wanting to memorize right away. Okay, we have in the middle of page 450, these are called properties of logarithms. You may look in other books and they'll call them laws, L-A-W-S, of logarithms. And sometimes I don't know if I use laws or properties, probably laws, but anyway. Okay, we have some properties of logarithms. and these are going to be properties that you memorize. But the first one, I want to do the proof for it so you know it doesn't fall out of the sky. All right. And before we do the proof, let's just plug a few numbers in the calculator to sort of verify this. By calculator, example. And remember, one set of numbers is not a proof, we're just kind of showing it. Let's look at the natural log of 6 and show that's equal to the natural log of 2 plus natural log of 3. Because 2 times 3 is 6. I'm just going to show with the calculator this property, that if you have a product of two numbers multiplied together, and in my case that would be a 2 times 3, that's equal to the natural log of 2 plus natural log of 3. All right, on my calculator, I'm going to plug in the natural log of 6, and that's approximately equal to 1.79. And I'm going to plug in natural log of 2, and that's about 0.69. And the natural log of 3, that's approximately 1.1. It's 1.0986. If I were just rounding to 2 decimal places, it would be 1.1. So when I add that to 0.69, that's going to be approximately 1.79. Just sort of verifying that when you plug and chug numbers, that's going to give you the log of a product, m times n. It's the log of the base a of m plus log to the base a of n. All right, but I like to do the proof on this because if you have some understanding where this is coming from, then the other properties make sense and it's easier to memorize. Okay, so I'm just going to go through the proof, and you can sit back and enjoy this. And if you're watching this by tape, do not fast forward. Okay, I want you to follow it because you can do it. All right, we got the log to the base a of m times n equals log to the base a of m plus log to the base a of n. And this may just make some of you decide to become math majors. All right, if you were trying to prove something you didn't know anything about, you always go back to what you do know. So we all know how to work with properties of exponents. And you know there's a relationship between exponents and logarithms. So I'm just going to come under here to get us started. I'm going to say let x be log to the base a of m. And I'm just going to pick y to be log to the base a of n. All right, so we don't really know how to work with logarithms at this point, but if this is a log equation, I know how to switch it to exponential form. So I would have that a to the x would have to be m. Doesn't that make sense, switching it? And this would be a to the y is equal to n. And when I look over that I'm trying to talk about a product, I would see that m times n would have to be a to the x times a to the y, right? If m is a to the x and n is a to the y, I could put it right here. And then you're all excited, I can look at your faces and tell, that you have a to the x times a to the y. You know in exponents, when the bases are the same, what do you do to those exponents? You add, when the bases are the same, you add, so you got a to the x plus y equals mn. All right, so what you've done is you didn't have a clue what to do with these logarithms. You switched it to an exponential form. You applied the properties of exponents that you understand, and then you go, okay, well, let me switch it back to log form. Switch to log form. Okay, so if I go from this exponential equation to a log form, it's going to be log to what base? A of mn equals x plus y. Well, what do we define x to be? Log to the base a of m, and y to be log to the base a of n. And this is a proof to tell us that really what is happening here is, remember, these are exponent kind of deals. It says that whatever your log is equal to is a certain exponent that was in the previous section. It says when I am adding exponent, I'm multiplying like bases. So when you multiply, you're going to add. All right, so that's your first property. Log to the base a of mn is equal to log to the base a of m plus log to the base a of n. Now, all of you are probably also saying, why are we doing this? This is, I don't really see a great future in this. Some of you are probably thinking that. Once you get into calculus, you're going to learn to do what's called logarithmic differentiation. And what's going to happen is you're going to have an expression that you got to take the derivative of, and it's awful. But if you convert it to logarithms using the properties, it's going to be a piece of cake to find the derivative. You could have a full page of a major mess trying to do the derivative, or you can use properties to write it in a simpler form. So you will see this all again in your calculus class. Okay, so there's your first property that you're going to memorize. Second property that you're going to memorize, log to the base a of m divided by n. Okay, we're not going to do the proof of this. It's the very same proof, except that what happens when you've got exponents with like bases, and you're doing division. What do? You subtract. And that's how you're going to get log to the base a of m minus log to the base a of n, because you're subtracting those exponents. All right, and again, you could put in some numbers and verify it with the calculator, but we're pressing forward here, and then we'll jump in some exercises. The third one is log to the base a of m raised to a p. Basically, you're looking at a base with an exponent raised to a power. What do you do when you have power of a power rule with exponents? What do you do with those exponents? A cubed raised to the fourth. What do you do with that 3 and 4? Multiply. So this ends up being p multiplied times the log to the base a of m. That comes from the power of power rule with exponents. Now, let me make sure that you realize that this is not equal to log to the base a of m, the entire thing raised to the p. It is log to the base a, and it's only the m that's raised to the p. You don't normally see it with parentheses, but it's only the m that's raised to the p, not the entire thing. Okay? Everybody doing all right? You all have happy faces like you've done all this before. Except I can't see the people on video. I assume everybody watching this is happy. All right? So those are your properties on page 450. We're going to put all this together in a minute with the exercises. Got a lot of properties here. Now I'm on page 453. 453. We've got a couple more properties. And I'm going to tell you in words what these properties are saying. All right, I'm going to start with property number 7 because I call this the common sense property. You have to have a little common sense to get this one. All right? Lots of properties, so write them down on note cards and practice, 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 and there will be a lot of exercises for you to practice. Okay, number 7 is my common sense property. If log to the base a is m, and that's exactly equal to log to the base a of n, you got logs to the same base on both sides, and you got an argument m and an argument n. Wouldn't common sense tell you that if you have log to the base a, that the m and n must be the same thing? Okay, so if you have log to the base a of m equals log to the base a of n, common sense tells you or the arguments must be equal. Okay, property number 6, you're going to use this all the time. Do you remember how when you solved an algebraic equation, you could square both sides of the equation, you could square root both sides of the equation, do unto one side as you did unto the other? Okay, of course, when you squared both sides of an equation, you might be introducing extraneous roots. Remember that? Anytime you square both sides of an equation, you have to check. Y'all are looking at me like you just zoned out. Okay, so I'm just going to say, recall algebra days. Right. The algebra days, you had, okay, if x is equal to 2, you could square both sides and get x is equal to 2 squared of 4. However, what you got to be careful is that whenever you square both sides of an equation, if I solve this, this looks like x is 2 or x is negative 2. But in my problem, x was really only 2. So anytime you squared both sides of an equation, you always had to go back and check for what they were called extraneous, extraneous or fake solutions. So anytime you squared both sides of an equation, you had to be careful about checking to make sure in the original problem it was true. Okay, well, similar to that, the fact that you can cube both sides, square root both sides, do whatever to both sides of an equation, property number 6 right here on page 453 says, well, if I have an equation, isn't this exciting? I can take the log to the same base of each side of the equation, and I still have a true statement. Okay, if I have two sides, if I have m equal to n, I can take the log of both sides of the equation. All right, let's do an example. Okay, I could have that 2 cubed is equal to 8. All right, so now I could say I'm going to take the log of 2 cubed, natural log. I'm going to take I can do any kind of log to any base. I use natural log so I didn't have to write so many letters. Lazy. Natural log of 2 cubed equals natural log of 8. All right, I'm going to go a step further and use my property says that's 3 times natural log of 2 is equal to natural log of 8. I'm just going to plug and chug on my calculator real fast just to verify this. Natural log of 2 is about 0.693147, and I'm going to multiply that times 3, and that gives me 2.07944, and natural log of 8 is 2.07944, same thing. Can you see it there on my calculator? The point was, if I have a true statement to start with, I can take log to any base of both sides, and I still have an equivalent equation. They both are still equal on the same side, just like if you square both sides, square root both sides, whatever. Okay? All right. Now, where's my other little identity I'm looking for? There's another little identity that I want to look for. Maybe it's in the next section. I don't see it. I didn't recall seeing it. Okay. Well, I'm going to give it to you anyway because you're going to love this one. Okay. This is another identity. That was like taking the log of both sides. This one is called, by the way, this is not in the precise Encyclopedia of Mathematical Vocabulary. I looked it up, but it does show up in papers. It's called exponentiate both sides of an equation. Exponentiate both sides of an equation. Here's the example. If I have log to the base 2 of, I have to be careful making this up on the spot. Log to the base 2 of x is equal to 3. All right, what you already know is that x is equal to 2 cubed, correct? All right, exponentiating both sides of an equation means that I can come through, because this is a log to the base 2, I can let both sides of the equation be the exponent for 2. Oops, I meant to do a 2 here. 2 raised to the log, I have to keep my bases the same. This is called exponentiating both sides. I let both sides of the exponent of the equation become exponents. And because I want to be able to use the identity we just talked about, 2 raised to the log to the base 2 of x, I use 2 for being the base where these are the exponents. So using our other identity we just talked about earlier, x is equal to 2 cubed. So another identity is if you have a log equation, whatever that base is, if you let both sides of the equation become the base for those exponents, you've solved the equation. And of course, for this particular problem, it would have been a lot easier to switch to exponential form, and you got it. But some problems, it's easier if you exponentiate both sides and get there. Okay? Yes. Comment was explain one more time. I want to back up and say one more time. Page 453. Basically, it says if you have an equation, you can actually take the log to some base of both sides and your equation is still equivalent. There's another property, which I can't put my finger on in your book and it may not be there, is where it says if you have an equation, especially if you had a log in it, you can exponentiate both sides of the equation, meaning that you have an equation, let's let both sides of the equation become the exponent for some number. And if it has a log in it, you would want to use your base for the exponential equation to be the same as your log so that that identity cancels that part out and you get your argument. Let's do one more. Suppose you have e exponentiate natural log of natural log of 5 equals 5 to the x equals 3, for example. Natural log of 5 to the x equals 3. Okay, if I wanted to for some reason, I could come under here. This is understood log to the base e. So I could let both sides of the equation become the exponent with a base e. Because e raised to the natural log of 5 to the x is 5 to the x from your properties, and that is equal to e cubed. Actually, that was a bad example because if I were trying to solve for x, it would have been better to bring the x down and then I would have had it. I was just trying to illustrate that both sides could become the exponent for base e to cancel that part out. Okay? All right. Okay, so back on page 453, you can always take the log of both sides of an equation, and then my input was you could exponentiate both sides. All right, one more down at the bottom, page 453. I hope you guys are wearing your book out. There's tons of examples worked out in great detail for you. Very important theorem. Very important theorem. You'll recall that your calculator only has common log and natural log. Only has common log and natural log. So how do you approximate when it's logged to a different base? And so you have a theorem here that says if I have a log to the base a of m and I want to go to an entirely different base, maybe that's common log base 10 or natural log base e, then this will be equal to log to whatever base you choose of m over log of that same base of b of a. Is that an a there? Log to the base b of a. All right, I'll show you how I remember this because that looks a little bit confusing. I'm going to show you a very unmathematical way to remember this. Okay, so this is easy. Change of base formula. Okay, and again, the reason you're going to even use a change of base formula is because your calculator only has common logs and natural logs. So if I had to find log to the base 3 of 5, okay, if I needed to find approximately what is log to the base 3 of 5, okay, I'm going to go with natural log. All right, this is an unmathematical way to do it, but this is how I remember it. According to our theorem, it's going to be natural log of 5 over natural log of 3. Basically, all you have to do to remember this is, see that's log to the base 3, so just put the 3 down in the denominator and the 5 in the numerator. It's kind of like you did a little line through here. That's not totally correct, but it helps you remember. So it's natural log of 5 over natural log of 3. Or it could be common log of 5 over common log of 3 if you wanted to punch in your calculator. So your change of base, you're only really going to go natural log or common log. So if you had log to the base 3 of 5 and you wanted to know what that's approximately equal to, change your base to maybe natural log, and it'd be natural log of 5 over natural log of 3. And you got it. What about log to the base 7 of 25? Change it to natural log. What is it? Natural log of 25 over natural log of 7. Okay, and this is the way I remember it. This is up in the numerator, and that one's going to be down in the denominator. Okay? Is that good? All right, you should be in brain overload with all these little theorems. There are so many of them. Actually, what I just did is over on page 454. 454 in the middle of the page. And again, this is because your calculator only has common log and natural log. Log to the base a of m, there it is with the common log, and there it is with the natural log. Okay, with lots of examples. All right, let's go to the exercises and work some problems. Okay, I'm on page 456. Everybody got all those properties at your fingertips? Tons of them. Okay, we're on page 456. And we're going to jump on problem number, let's just pick some. Okay, we'll do number 14 for our first problem. It says log to the base 6 of 9 plus log to the base 6 of 4. The instructions are to use the properties of logs to find the exact value of the expression. Do not use the calculator. All right, our property says that we have log to the base 6 of 9 plus log to the base 6 of 4. And we're remembering this is talking about exponents. This is going to be equal to log to the base 6 of what? 9 times 4. Okay, so we have log to the base 6. 9 times 4 is 36. Can we simplify this further? 36 is the same thing as 6 squared. And what happens when you have log to the base 6 of 6 squared? That's equal to 2. Okay, so the log to the base 6 of 9 plus log to the base 6 of 4 is log to the base 6 of 36. 36 is 6 squared. So I've got bunches of properties going on here. There's the first property of logarithms that say when you add with like bases, you multiply those arguments. And then this was your identity. Log to the base 6 of 6 squared is 2.
Why is it 2?
Why is it 2? Your identity,
Oh, no.
Second.
because they're composition of functions. Do you remember that?
The second identity.
Second identity I gave you And it's also on page 449, number 2, log to the base a of a to the r. I know, too many at one time. So, good question. All right, is that good, everybody? Let's go to number 22. 22 is e raised to the log of e squared raised to the 9th. E raised to the log of e squared raised to the 9th. I need some help here.
Well, we can do it.
Well, that's an e squared right there. What you gonna do?
Wouldn't you just change it to ln and then you'd have the ln of 2? And then, never mind, I'll just shut up.
I'm not sure what you're going to do. I'm not sure what his point was in this problem, to tell you the truth. My thought was to go e to the log of e squared to the 3 squared. And because this e squared here is bothering me, I'm not quite sure what he has in mind. Am I reading it right?
No, that's fine. I'm great.
I'm not. I'll look that one up and figure out what he's. I'll talk about that tomorrow. I'm not quite sure what's going on right there. Okay, let's look at number 16. Number 16, log to the base 8 of 16 minus log to the base 8 of 2. What's your property going to be here? You got subtraction, so it's going to be
Multiplication.
subtraction, division, log to the base 8 of 16 divided by 2, which is log to the base 8 of 8, which is like log to the base 8 of 8 to the first, and everybody says that is 1. Okay? All right, so they just wanted to get you going on some properties in there. Okay? Everybody good? Let's go to number 52. Write as a single logarithm, which just means use all your properties to write as a single logarithm. 2 to the log to the base 3 of u minus log to the base 3 of v. Be careful when you're using v so you can tell the difference. And it wants us to write it as log to the base 3 of something. How are you going to deal with this 2 that's in front of log to the base 3 of u? What does that 2 become? Where does it go?
Exponent.
That's the exponent for the u. That's property number 3. So we have log to the base 3 of u squared, property 3, minus log to the base 3 of v. All right, what property am I going to use next to write this as a single log?
Log 3.
You can add or multiply them.
Okay, there's a subtraction sign here, so you're going to divide. So that's really property 2. So it's log to the base 3 of u squared divided by v. All right, the instructions said write this thing as a single logarithm. I had 2 terms. I had to find a way to simplify it to a single logarithm. Okay, before I could do the division, I had to take care of the 2 that was out front. That was your property 3 to get it to the exponent. Now it fit the form for property 2. Can you go directly from step 1 to step 3? No, because his question was, why couldn't you skip that middle step? The reason is that when you go back to your properties, it is 1 times the log of a to the m minus 1 times the log of a to the n to get to here. And if there's a number in front of that log, you have got to work on property 3 to get it to log to the base a of m to begin with. Okay, again, there's only a 1 in front of each of those, not some other number. Okay, thanks for asking that. All right, everybody good? Okay, next example, that was number 52. Need to practice lots of these because you could get confused on them. Number 59. Same instructions. We want to write as a single logarithm. So we have 8 log to the base 2. I'm going to write that as a 3x minus 2 to the 1/2 power, even though it's got a square root in the book. Minus log to the base 2 of 4 over x plus log to the base 2 of 4. Okay. All right, we have 3 terms here, and we need to write it as a single log. 3 terms to write as a single log. Okay, I will tell you that my hint is that when you have more than 2 terms, group all positives together and all minuses together. In other words, get the positives together and get the minuses together instead of plus, minus, plus. That's my hint. That makes things work nicely. You don't have to do that way, but it usually saves you a little trouble. So we'll have 8 log to the base 2, 3x minus 2 raised to the 1/2, plus log to the base 2 of 4 minus log to the base 2 of 4 over x. Okay, and if I had a bunch of minuses, then your next step would be to factor out the negative and do that grouping there. Okay? All right, let's see how we're going to deal with getting this to a single logarithm. All right, how are you going to deal with that 8 out in front of log to the base 2? In the end, I want log to the base 2 of one thing. So how are you going to deal with this 8?
Put it on top of the 1/2, multiply by 1/2.
Yes, I'm going to carry the 8 back up here and multiply it times 1/2. So I'll have log to the base 2 of 3x minus 2 to what power now?
4.
4. Half of 8, 4. And somebody tell me right away how to simplify log to the base 2 of 4. How am I going to
2
simplify that?
2 squared.
Okay, 4 is the same thing as 2 squared, correct? Log to the base 2 of 2 squared. What's that going to be equal to? 2. Right? I'm not sure that I wanted to do that since they told me to put this as a single log expression. Maybe I better not simplify that. Let's keep going and see what happens. All right, so I think they must want us to keep it that way. I'm not quite sure why they use those numbers. I would have changed that to a 2, but they want the final answer to be log to the base 2 of something. All right, so let's keep that in the way it is. What are you going to do when you have log to the base 2 of something raised to the 4th plus log to the base 2 of 4? What are you going to do with those arguments?
You're going to multiply.
Yeah, you are. You're going to multiply them. So if I'm trying to keep log to the base 2, this would be 3x minus 2 to the 4th times 4, same base. And then what do you do when you divide? I just told you the answer. When you subtract, you're going to divide 4 over x. So it's log to the base 2 of this entire expression. And we're going to clean up inside there. We'll have log to the base 2, 3x minus 2 to the 4th times 4, and inverting and multiplying, we'll have x over 4. Did I run off the page? I just divided by 4 over x is invert and multiply by x over 4. And now we'll see that the 4's divide out. when I flipped over inverted the 4 over x, the 4's divide out. And because I ran out of space, I'm going to stick it right here. So we have log to the base 2 of x times 3x minus 2 raised to the 4th, because the 4 is divided out. Okay, they were about to throw me on this log to the base 2 of 4 because it is equivalent to 2, but because the instructions said we only want everything written as a single log, I didn't need to convert that to a 2 there. Okay, all right. Who did I lose? Sarah, can I help?
I just can't see the last.
This part right here? I'm sorry. When I inverted the 4 over x, I have x over 4, and the 4 is divided out. And then I was running off the page, and I did a very bad thing by sending it back over to here. Okay? And I would get mad at you if you did sloppy stuff like this all over your paper. All right? Everybody good? All right, let's try another example. My next example is number 63. Number 63. We're still writing as a single log expression. 63. 2 times the log to the base 2 of x plus 1 minus log to the base 2 of x plus 3 minus log to the base 2 of x minus 1. Okay, I picked out this example because you've got 2 terms with negatives here. 2 terms with negatives. And if you recall my hint, you want to be sure to group all the positives together and all the negatives together. All right, so we have 2 log to the base 2 of x plus 1. And now let's factor out that negative. Log to the base 2, x plus 3 plus log to the base 2 of x minus 1. This is what I mean by grouping. Get all your negatives grouped together and all your positives grouped together. You don't have to do it this way, but it's going to save you a step, and it's also going to save you a headache. If you have divided by, it gets to be a mess. All right, so our instructions are to write as a single logarithm. How are you going to deal with the 2 out front? That becomes your exponent, log to the base 2 of x plus 1 squared. All right, let's go inside parentheses. If I have log to the base 2 of x plus 3 plus log to the base 2 of x minus 1, that's equal to log to the base 2 of x plus 3 times x minus 1. Okay? All right, so when I brought the 2 as the exponent on the first term, that was property 3. And when I multiplied, because these 2 terms were added, that was property 1. All right. Now, what am I going to, I now have log to the base 2 of something minus log to the base 2 of something else. What are we going to do now? Divide. Log to the base 2, the numerator is x plus 1 squared. The denominator is x plus 3 times x minus 1. Okay? And normally you don't use any kind of brackets or anything, but this really is log to the base 2 of this whole thing, x plus 1 squared over x plus 3, x minus 1. And the reason I write that is some people will put the log to the base 2 of the numerator over log to the base 2 of the denominator, and that's not true. It's log to the base 2 of this whole expression. Okay.
Like on a test or something, can we write it with the brackets?
You can absolutely write it with the brackets. Anytime you're in doubt, stick it in. Absolutely. I think it's clearer like this, but you don't normally see it like that, but that's perfectly perfect. Okay? Everybody good? All right, let's do a change of base formula. This is problem number 66. Number 66. Log to the base 5 of 18. And let's go to, do y'all want to do common logs or natural logs? Your choice. Natural logs. All right, convert this to natural logs. What would it be? Natural log of 18 over natural log of 5. And if I wanted to find out approximately what that is equal to, I'd have natural log of 18 divided by natural log of 5. And that comes out to be approximately 1.796. Natural log of 18 divided by natural log of 5. This is an exact answer, and that would be just fine on a test. Anybody can plug and chug natural log of 18 over natural log of 5. Everybody good? All right, we didn't get nearly where I was hoping. So tomorrow we're going to look at 4.7, hopefully 4.8, and 4.9. And then we'll be to the cumulative review again. Listen very carefully to go ahead and start working on your cumulative review on page 501, the cumulative review, and you will be omitting number 10C. You'll be omitting number 10C and number 15. And I would expect that it will not be tomorrow, which is the next 2 lessons on video, but the day after. So for you guys, that would be Thursday. That's what I'm expecting. Okay? All right, have a great day, everybody.